Welcome to the third and last lecture in this series on structural analysis. After we introduced component and service models and graphs to describe the structure of a system, in this last lecture we are using that to analyze how faults can propagate from lower level components up to system level. We are going to use two different approaches. The one is called the fault tree analysis, and the second is the fault mode and effect analysis. Both are extremely popular and used in the industry. Let's start with the first one, with the fault tree analysis. So you remember that when introducing the component and services model, we had a drawing like this one, where hierarchically we shown how different components make part of subsystems and how different subsystems are connected to provide overall functionality of a system. And when you draw a graph, a layout like that, a block diagram like that, you realize that it is a graph and it is a tree. Along this tree, it's really easy to see how the presence of a fault at a lower level can propagate up to subsystem and system level. The idea of fault tree analysis is actually to formalize this. In order to do that, we assume that we have a knowledge of these components and these services and how they are interconnected. And we can start with a very simple example, the one of a light bulb, a switch, and the power supply. So we start with the power supply. So we assume we have a battery. And this is connected via an electric circuit to a switch. And this is connected to the light bulb. And then we have the return wire. So everything is connected to earth. So safety first. And let's write down power. Switch is here. It's normally open, but we can close it. And light bulb is here. So in normal conditions, what we want is to close the switch and get light. But in order for this to happen, we need that all the components are working. So we need that the power, the switch, and the light bulb, they need to work, and we can represent these using a logic function. And this logic function is simply taking the end. So if power is working and switch is working and light bulb is working, we get light. Otherwise, we don't. So what I have drawn here is a way of representing conditions for the system to work. And this logical condition is using a positive logic. So it is propagating forward information on components working. If this is healthy and working, if this is healthy and working, if this is healthy and working, if everything is working, then you have light. This way it is easier to understand the concept now, but be prepared in the fault tree analysis that we are introducing in this lecture, the opposite point of view is used. So instead of asking whether a component is working, the fault tree analysis is asking whether a component is not working. So we can easily turn this around anyway. So we can ask if power is faulty, or the switch is faulty, or the light bulb is faulty, then we have no light. Okay, that was rather intuitive. So if we switch from positive to negative logic, all we need to do is to change the AND into an logical OR, which is denoted with this symbol, OR. So this is the way to represent the same reasoning in negative logic. Either the power is not working, or the switch is not working, or the light bulb is not working, then we don't get light. And in this case, it is occurring because if you look at the structure of the system, it is a series structure. You have power supplying the switch, supplying the light bulb. So if just one of the components along this chain is not working, the entire chain is failing. And the OR is exactly encoding this. You need at least one of these to be true. True means not working. That this output of this logical gate is true. So no light. So this was an intuitive example. So if we want to do this same kind of analysis for a more complex system, we need just a little bit more of formalism. And we need to introduce what is called a fault tree. So a fault tree actually is not really a tree from the graph point of view, but it is a directed acyclic graph. So there are no cycles, but it is not true that it is a tree. And in this example, you see immediately that this is not a tree, because you can go from this node up to this node here, either following this left path or following this right path. The only important thing is that there are no loops. What is encoding this graph? So this graph has nodes that are called, in this case, leaves. And these leaves represent failure of a given component. So in the previous example, we had leaves representing the failure of the power, or the switch, or the light bulb. We have also other nodes that are logical gates. So the leaves represent basic failure events in individual components. But the logical gates represent how failure of these components can propagate up. In the case of the light bulb, we had only one logical gate. It was an OR. So any component failing will propagate up to the system failing. This example is a bit more complex, so we have also AND gates, and this specific special kind of OR gate, where you see there is a 2/3. This is a gate that is telling you that in order for the gate to output a true value, you need that at least 2/3 of its inputs are true. Why you should need something like that? Well, in this example taken from a computer system, we can see in which conditions we need this kind of gate. These represent a computer system. And the computer system has several subsystems. We have memory at this lower level. We have CPU here. We have a bus that is connecting the CPUs to memory and to other components. And we have a power supply. And then we have some control unit. I don't know, the keyboard and mouse of your computer, or simply the main switch. And then we have a top node here that represents the system. So it is like the hierarchical description we introduced before. At the top, you have the system, and at lower level, you have subsystems and components. In this example of the computer, they assume that you have a number of memory units that are redundant. So there is some error correction mechanism. So you actually need only 2 over the 3 memory subsystems to be working. If just one is not working, you can reconstruct what data should have been by using some error correction code or parity relation. If you don't know what this is about, don't worry, that's about computer architectures. But anyway, the thing is, if 2 are still working, then the memory subsystem is working. Or turn the other way around. For the memory subsystem to be not working, you need at least 2 memory components to be not working. And this is precisely what is encoded here. Because remember that we are working in negative logic. So we are propagating up logical values that represent the component being failed. So if 2 memory units are failed, this is enough for the memory subsystem itself to be failed. And if it is failed, well, this is going to be bad, because you see that the memory is entering OR gates at all levels here. And this represents the fact that a computer cannot work if the memory subsystem is not working. In this example, we have also the CPU, and we assume that we have 2 redundant CPUs. So at least one of the 2 CPUs should be working. How it is encoded in the graph? So it is encoded by having 2 different branches here, one representing the first CPU not working, sorry, and the other the second CPU not working. In both cases, we have a leaf that represents the power supply. So this is a possibly confusing feature of fault trees, but the same component can appear many times. So the power supply actually is a component that you obviously need for the computer to work, and it is not redundant, so there is not a backup power supply here. So the way that this was encoded in the fault tree was to include the power supply as a leaf, both in this branch and in this other branch. So this means that if the CPU number 1 is not working, or the power supply is not working, then this branch will propagate forward, upward, a true. So this branch not working. Or if the CPU number 2 is not working, or the power supply is not working, also we have a true. True means not working. As the power supply is appearing in both branches, when the power supply is broken, both this branch and this branch will propagate a true. And you see that these branches are connected here by an AND. So what happens? If CPU 1 is not working and CPU 2 is not working, you have both a true here and here. This AND will propagate upward a true. And that's indeed what we expect. So if we have 2 redundant CPUs in the computer and both are not working, I expect that this should propagate upward and the entire system is not working. Indeed, that's what's happening. If the memory is not working, both branches will propagate a true, so the system is not working. And if the power supply is not working, again, both these branches will propagate a true upward, and the system is not working. So hopefully that was the intuitive way to represent and introduce the fault tree analysis, but we can formalize that a little bit, because for more complex systems, we need formal tools. So let's define things. The first thing we introduced are events. Events in the fault tree are represented by binary variables. and we work in negative logic. So true means a failure and false means healthy. And these events are combined and propagated using logical gates. So we have an AND where the output of AND is true if all the inputs are true. We have an OR where the output is true if at least one input is true. And then we have the K over N or majority voting. So this is true if at least K inputs are true. So these are the basic components of the fault tree. The fault tree itself is defined formally as a tuple with 4 elements. The first element is the set of basic events. So the basic events are the failures of individual components. So what we called in the graph the leaves of the tree. Then we have a set of gates that are combining the basic events. And then we have a description of the gates. So T is describing which kind of gate we have, N or not, or K over N. And then finally we have a maps, I, that maps the gates to their inputs. So this is describing the edges of the graph. So in this graph, in the fault tree, we have 2 different kind of nodes. This is describing the second kind of nodes, and this is describing the connectivity, the edges in the fault tree. Now that we have a fault tree defined, we also need to define how we are going to evaluate it, because this is what we want to do. So we want to have a set of basic events that is a set of logical values, true and false, and if we want to evaluate if the entire system is failed or not. So we want to evaluate what is the logical value of the top node, the one representing the system. And to do that, we introduce a function that is actually doing that. So a semantic function that operates on all the possible basic events and all the possible values of the gates to provide a single output. That is 0, the system is not failed, or 1, the system is failed. We can also use a shorthand notation for this. And then there is an important concept, the main concept in the analysis of a fault tree, which is the concept of the cut set and the minimal cut set. So a cut set, C, is a subset of the basic events such that the semantic function is true. Translated to normal language, a cut set is a set of critical components. If they are failed, the system is failed. A minimal cut set is a cut set that is critical in the sense that if you remove at least one component from there, the system is no longer failed. So we can go back to the example for the computer and look for minimal cut set. A minimal cut set, in this case, is comprised by, well, the main switch of the computer, so if you're using it or not, and the bus. So sorry, we didn't talk about the bus previously, but also the bus, you see, is a critical component here. If it is not working, the entire computer is not working. But it's easy to see that you can find another minimal cut set if instead of the bus, you consider the power supply. So the power supply and the fact that we are using the computer is leading to system failure. So this leaf here may seem a bit redundant. So why we need that? Well, it is for well-posedness. So as we discussed in one of the online meetings, if I have a system that is not powered, even if there is a fault inside the system, this is not going to lead to a failure of the system. So I can see that the system is failing only when I'm using it. So this is why I have this. But indeed, is a bit redundant. We can also find some cut sets here. For instance, M1, M2, M3, and U is a cut set. But it is not a minimal cut set, because indeed we know that there is some redundancy in the memory units. If two memory units anyway are not working, the entire memory subsystem is not working. So having a cut set with all the three is too much. We know that it is enough to have two memory units not working. So indeed, a minimum cut set is this one, U, M1, and M2. So you can try to find other cut sets and minimum cut sets in this example to try to get a better grasp of the concept. Anyway, there is also a formal way, an algorithmic way, to find a minimum cut set. To do that, we need first to introduce another function, that is the structure function f. So this function tells that when we have a failure at the top level, based on the values of the fault state of the individual components. So the inputs of this function are a set of logical values, one for every basic element in the system. So in the case of the computer system, we have 1, 2, 3, 4, 6, 5, 7, and 8 arguments to this function, 8 logical variables that can either be 0, the system is working, or 1, the system is not working. And this function will simply tell you, okay, given these vector of Boolean variables, the value of the system failure is either 0 or 1. So either we don't have or we have the fault at the upper level. Now, the key thing is in expressing this function, which is a logical function, in a special form, a form that is called a disjoint normal form. When we do that, it is automatic to get the minimum cut set. So a disjoint normal form is a form where your function is expressed as a series of OR of individual terms that are made only of AND. So something like that. E1 and E2, or E3, or E4 and E5 and E6. This is a disjoint normal form. So we have OR applied to individual terms that only contain AND. So considering how the OR operates, if at least one of these terms is true, then the entire function is true. But for one of these terms to be true, all the individual argument needs to be true, because this is a AND. So you immediately see that this identifies a minimum cut set. Because for this to be true, I need component 4, 5, and 6 all together to be faulty. If this happens, the entire function evaluates to true, which means that we have system failure. So let us see this a bit more in detail. This is indeed what I just said. So the disjoint normal form is an OR of individual conjunctions. Now the question is, how can I get a form like that? You can get that by a simple manipulation of the logic function. And you use a couple of tools, theorems, that are called the De Morgan's laws, and they allow you to take a conjunction and turn that into a disjunction, or take a disjunction and turn that into a conjunction. You can also visualize these from a set point of view. Maybe this is more intuitive. So if you have a set A and B, the end of A and B is represented by the intersection here. And the OR is represented by the union. So we can see that if we take the union A or B and we compute the negation of that, we get this blue part. And this blue part is indeed the intersection of what? The intersection of the negation of A, so everything that is outside A, intersected with everything that is outside B. And indeed we get this. And similarly, you can visualize the other case. When you are interested in the negation of the intersection, what you get is all that, which is the negation of A united with the negation of B. Okay, so we are not going into the details of the manipulation of the logical function, but as an interesting exercise, you can do it yourself for the computer example. Also, we are not going into more advanced topics on the fault tree analysis. One topic we're not covering are probabilistic fault trees, where instead of having sharp logical values for the failure of a component, we have probabilities of a component failing. We are not looking at dynamic fault trees, repairable fault trees, where you introduce the possibility to repair a component, and so on. Now let us cover the second part of today's lecture. And it is about the failure mode and effects analysis, FMEA. So the fault tree analysis provided us a binary description of the health status of our system. So we had components that were either healthy or faulty, and we had the entire system that was either working or failed. If we want to know not just if and when a system is failing, but why and how a system is failing, we have another tool to look into, and indeed is this the FMEA. So the FMEA is propagating upwards not just the health status, but the presence of a given fault and the effects that this fault has on other components. So for instance, we have this component here that can fail in two different ways, and these two different ways are leading to two different effects on the other components at higher level. And we see how these components can propagate up to the system level, unless we have a way at lower levels to stop one of the effects. In order to introduce this, we can use the same example with a light bulb. So in the case of the light bulb, we know that any of the three components failing will lead to the entire system failing. But how? Well, if you look at a power system, we can have a first fault that is due to the battery being drained. So no more juice in the battery. And this is causing an effect at this level, and the effect is we have no current. if we have no current at the input of the switch, we have no current at the output anyway. And if we have no current out of the switch, we have no current going through the light bulb, so we have no light. And this is the final effect at the system level. Similarly, if the switch is stuck open, the effect is having no current going to the light bulb. And we get no light. So as we can see, two different faults in different components are leading to the same effect at a higher level, and both leading to the same way of failing of the system. But actually, there is a third way for the system to fail, and it is when we have a broken light bulb. And of course, a broken light bulb will lead to the same final effect, no light. And so we see that we have two different actors that we introduced on this stage. So the first kind of actor that we introduced is the internal fault. These represent what in the fault tree analysis was the basic event. So one component not working. And as examples, we have the battery drained is an internal fault. We have the switch stuck open. It is an internal fault. And the broken light bulb, it is an internal fault. But we have also another thing. We have the propagated effect. So the fact that we have no current on the switch because the battery is drained is a propagated effect. So it is a failure of a higher level component in providing its service that is due not to a fault local to that component, but to a fault that happened in a component that is lower in the hierarchy of the system. And similarly, the fact that we have no current going to the light bulb because of the drained battery is again a propagated effect at yet a higher level. The fact that we have no current because the switch is stuck open is another propagated effect. And here having no light because the broken light bulb, well, this is a direct effect that is because of the local fault on the light bulb. So you may wonder at this point if there is a formal way to describe how local faults get propagated at higher level through effects. And indeed, there is one. Intuitively, we can draw something like this, yet another graph that is encoding this propagation. So we have three components here, and we can then consider three levels. So the power level, the switch level, and the light bulb level. And finally, let's say the light level. So the intended functionality of the entire system is to produce light. If at the power level we have the battery drained, this is a local fault, and this is going to cause at the switch level that we have no current. And this is a propagated effect. But at the switch level, we also have a local fault that is the stuck open fault of the switch. But they are going to cause at the light bulb level the same effect anyway, no current, which is propagated, of course. So let us introduce some edges then to show the connection. So battery drained, no current. No current because of battery drained, no current at this level. But stack open, no current at this level as well. And finally, at the light bulb level, we have the broken bulb, which is a local fault. And both at the higher level will cause the final effect of no light being produced. And the connection is like this. So broken bulb, no light, no current, no light. So you see, interesting, the structure of this graph is that we have some parts that will merge. So battery drained, no current, is merging with stack open, no current. And no current and broken bulb here will merge into no light at this level. So this tells us that an effect that we observe at the higher level has no unique explanation in this case. It is ambiguous. So if we know that there is no light and we want to do a root cause analysis, we have many possible solutions, because either we have a broken bulb, either we have a stack open switch, or we have a battery drained. And if you remember when we mentioned in one of the first lectures, troubleshooting sections of manuals, they are describing in verbose terms actually these. They tell you which possible faults can cause a given symptom that you experience at a higher level. And then they provide you a list of things that you can try. In this case, the manual will say, if there is no light, check that the power source is working. And then check that your switch is closed and it is working and not stuck. And finally, check if your light bulb is not burned out. So if you check all these conditions, then you are guaranteed, in this case, that you're going to find out the fault and correct it. This kind of intuitive representation that I used is not the one that is normally used to do the FMEA analysis. There is another one in the book by Blanke that is not an orthodox graph, but it's more effective. So we are going to use it. In this representation, we have one box, one block for every component. And this block is divided into two sections, one for local faults and one for effects that are propagated. For instance, in this case, we have a first block for the power. And this block has only one fault. That we are going to denote with F1. And this fault is the drained battery. Then, at the switch level, we have both local faults. We will call F2 the switch open fault. But we also have effects propagated from the battery level. So we have effects. We have one effect that we call E1. And this is no current because the battery is drained. So in order to visualize this, we are introducing a connection from this fault to this effect. So this is the propagation of E1. Then, at the light bulb level, we have one local fault, the broken bulb, that we call F3. And we have one possible effect that we call E2, that is no current coming in. And this can be due to both the fact that the battery was drained and this propagated the effect to the switch and propagated it to the bulb, or can also be due to the local fault of the switch. So we put nodes here to denote that. So the merge that we highlighted is actually denoted like this. So we have a line coming from here and from here, they merge both on a single line that represent the effect no current out of the switch propagating to the light bulb. And finally, we have one last effect that is E3 that represents no light out of the light bulb, and this is due to both, can be due to both a fault at the light bulb level or an effect propagated from the lower levels. So this is a way to denote it using the notation in Blanquet's book, and this is the one we're going to use. So now that we introduced symbols for the faults and the effect, we can actually formalize this analysis, realizing that what we have done is to do a Boolean mapping, so to find a function whose output is either true or false, between what? Between a vector of possible faults and a vector of possible effects. So we had the faults 1, 2, and 3, so a vector with 3 components. Each component can either be true or false. And then we have a vector of effects, effects 1, effects 2, and 3. We can represent this propagation using this operation, this Boolean operator that is a sort of multiplication. And it tells us that the effect E can be computed by doing this Boolean multiplication between the fault vector and this matrix M. This matrix M is the matrix that is encoding how faults cause effects. And the interesting thing is that this operator is implementing a disjoint normal form as we had in the fault tree analysis. So it's the same kind of thing. The only difference with the fault tree analysis is that now we are keeping track of which fault was propagated to which effect. And in full, the definition of this Boolean operator is this one. So the component I of the effect vector is equal to what? This disjoint normal form, where we have every conjunction term is equal to the matrix M row I, so the same row as the effect, component 1 that is conjuncted here, so we take the AND with the fault number 1, or the M matrix row I column 2 and the fault 2, and so on. So we take the row number I of this matrix, and we take the AND of every component of that row with every component of the fault vector. And the result is put into the first component of the vector with the effects. So to get a grasp of this operator, we can just apply that to the example with the light bulb. And so we start computing the matrix M and the relation between effects and fault at this level, at the level of the power. So the power level, we have that the first effect, E1, is equal to simply 1 and this Boolean times fault number 1. It is very simple because here we have only one possible fault and only one possible effect, and we know that the effect is caused by the fault. So we have this mapping. At this level, what we have is that E2 is equal to, well, we know that it is either due to E1 or due to F2, so we write that this way. With a matrix that has only one row with only ones, and we do this Boolean multiplication with a column vector with the local fault of the switch and the propagated effect E1. And so if you remember the definition, this simply means that E2 is equal to F2 or E1. So both they are causing the same. And finally, the same kind of matrix is defining how the effect number 3 is mapped to the local faults and the propagated effects at the light bulb level. So we have F3 here and E2 here. Okay, so this is the mapping between faults and effects at each component. But actually, we would be interested in a mapping between E3 and the individual faults. So in order to do that, we simply need to do a substitution starting from the last level. So in E3, we see that we have E2. But E2 can be computed in terms of F2 and E1. And E1 can be computed in terms of F1. So if we start from this expression, we replace the expression for E2 here. And then we will get something that contains E1. But if we replace E1 expression in what we got here, in the end, we need to have finally our mapping between the final effect E3 and the local faults F1, F2, and F3. And so this is what we're going to do now by looking at how to expand expressions like that. Because actually we had this kind of expression, the effect, the local effect out of a component is due to a local propagation matrix that do this multiplication between local faults and propagated effects from the ancestors, so the components at the lower level. So the way to recursively expand this is to do this expansion. So we take the effects from the ancestors, and we know that they are computed how? So the effects of the ancestors are computed similarly with a matrix of the ancestor that multiplies faults at the ancestor level and effects from the ancestors of the ancestor. So let's write ancestor squared. So we take this and we replace it here, and what we get is this expression. So the local matrix that we had here that multiplies a block diagonal matrix with identity and a matrix from the ancestor that multiplies the local faults of the component and the faults of the ancestors. Actually here in this expansion, I was not assuming there were also effects propagated from ancestors of the ancestors. But if it happens, no problem. You just need to take this in place of this in place of this, and then you do another iteration of expansion. So you expand until you get to the basic level and there are no more ancestors. Another interesting thing that you can do with the fault mode and effect analysis, is the reverse analysis, the inverse. So what we were doing now with this operator was to find a way to propagate forward faults to effects. But usually we are more interested in the opposite information, like in the troubleshooting section of the manual. So if we have a set of symptoms of effects, we want to go back and track them to root causes, to faults. So we can do that actually using another Boolean operator that is this other kind of product that we denote like this. So a sort of circle dot product. And we take this dot product between the transpose of the fault and effect matrix and the effect vector. So the result is a vector of faults that are candidates for explaining the effects that we see. So you need to consider that in this case, this vector is containing a 1 in the position of the effect that you experience. So if you have a complex system where there can be different effects, like you can have no light, some strange noise, some strange vibrations, there are the possibilities. But the only thing that you see is no light, then E should be equal to 1, no light, 0, because you don't hear any strange noise, 0, because there are no strange vibrations. So this is the value that you need to put here. And when you do that, and you do this dot product with M transpose, you get a vector F that, again, we have some zeros, at some point some ones, and these ones corresponds to the fault that explain this effect here. And the way that this dot product operator is defined is here. You do a comparison between the value of the effect and the value of the M transpose component I and 1. And then you take the AND with similarly a comparison between E2 and M transpose component I and 2, and so on. Basically, it is like saying, I know that for this effect, I need to have this, and this fault present. So I'm checking, do I have this effect and that fault present? And do I have that effect and this fault present? So if all of them evaluate true, then you know that that fault is the one causing it. Said in another way, let us assume that a given fault in your set of possible faults is causing 3 different effects. If only 2 of these 3 different effects are present, one of these comparisons will give you a false. And when you take the AND of everything, you get a false. So the only way to say that that fault is the culprit is if all those effects are indeed present. You can also have more than that present, but those should be. And now I will present you an example that is slightly more complex and also more relevant for this period of the year. And this example is about the robot that is picking up your Black Friday shopping.
Dematic Rapid Pick XT is a goods-to-robot piece pick system ideal for e-commerce fulfillment, retail store replenishment, and wholesale distribution applications. It is engineered for speed, so order processing time is compressed. It's accurate, pick the correct items in the right quantities. And it's efficient. because inventory storage and order assembly are completely automated. This drives costs down and productivity up. Here's how it works. Inventory is received and staged in a high-density automated storage subsystem. Typically, there is one SKU per tote. Multiple SKUs are accommodated in totes with compartment dividers. The Dematic warehouse execution software releases inventory totes in a strategic sequence. The tote arrives at the robotic pick position at the precise time it's needed to assemble the order. The number of robotic picking cells is determined by the required capacity. Robotic pick cells can be scheduled to operate 3 shifts a day during peak seasons. The overhead vision system captures an image of the items inside the inventory tote. The robot picks the item and places it into the order tote. A continuous flow of inventory totes supports high order picking rates. At the same time, empty order totes flow into position for loading. When all items are picked, it flows out of the robotic pick cell, then to packing and shipping. After the robotic pick process, inventory totes flow back to the automated storage subsystem and remain there until released for another order. The results are measurable: maximum productivity and efficiency, operational flexibility, and scalability for today and tomorrow's order fulfillment demands.
So in the video that we have just seen, there is a robot similar to this one. It is a picking robot. It has some machine vision sensor, for instance, a 3-dimensional camera, that can see where objects, where packets are on a conveyor belt. By using motors in the robotic arms as actuators, by using encoders in the joints as further sensors, and by using a gripper as another actuator, the robot can position itself on top of an object it wants to pick up, move down, close the gripper, and pick up the object and put that in some other place. So if we want to do an FMEA on this robot, we can start by considering all the possible faults and effects that we can have. So we start with a picker that is the end effector of the robot. And this component can have one local fault. So motors are damaged. And if the motors are damaged, the effects are that either the picker is not able to grasp, so no present is picked up, or it is picking another packet. If we look at the camera, we have 2 different faults we assume here. The 3D camera can either be offline, so it's not powered up, or the connection cable is defective, or the 3D camera can be uncalibrated. So which kind of effects we have? So if the camera is offline, no position measurement is provided, so there is no information about objects in the field of view of the camera. But if the camera is uncalibrated, what we get is a position for the objects that are in the field of view, but this position has an offset. And you can imagine this is bad, because it will mean that the robot will go and pick up another packet, possibly. If we look at the encoders in the joints of the robot, we have 2 possible faults. One is that one wiring is loose, and one is that the limit switch on the joint is stuck. So every joint has a safety feature, is a limit switch. So when the joint is getting up to the limit position, where no longer can move, there is a switch, an electric switch, saying don't move the motor forward, because otherwise you're damaging the joint. Which kind of facts we can have out of these 2 faults? If we have some issue with the wiring of the encoder, we can have a position offset in the measurement provided by the encoder. But if a limit switch is stuck, we have that the entire robot is stuck in the current position because it thinks it can no longer move. Finally, we consider the controller. So the controller itself is not failing. So we assume it is an electronic component that is sturdy and will not fail. But the effects that we can have out of that because of propagation from other components are that wrong position is sent to the motors or no position is sent to the motors. So actually how these faults and effects are connected together now is going to be shown in this next slide. So we have the components here and the description of the faults and so on. And at this point, we can start drawing the kind of graph that Planck is using. And we start at a lower level with the camera and the encoder. So the camera has two faults that is leading to two effects. So we have it here. Offline and uncalibrated are the faults. The effects, no position, position offset. So if we have no position or a position offset, and these are fed to the controller, what is happening is that either we have no position sent to the motors, if we have no position from the camera, or a wrong position is sent to the motors, if we have a position offset in the measurement from the camera. So we have these two effects mapped here to two effects out of the controller. For the case of the encoder, we have two different local faults, so loose wiring and stuck limit switch, and they are causing respectively a position offset and a stuck position. If this is going to the controller, these two effects are propagated as well. So when we have a position offset in the encoder, it gets propagated out of the controller as a wrong position sent to the motors. So we have this here. But if we have a stuck limit switch out of the encoder, and then we have the safety feature triggered and the robot doesn't move, then the controller is no longer sending other position commands to the motors, so this gets mapped to the second effect. And finally, at the peaker level, what's happened? We have one local fault that is a damaged motor. This will cause as an effect that there is no peaking. But no peaking will also occur if we have one of the controller effects propagated. So no position sent to the motors, because then the robot is not moving. But also if we send the wrong position to the motors, because if the robot moves into a position when there is no packet to be picked up, then the effect is that we don't pick any packet. The second effect that we can have out of the picker is that we are picking another packet. And this can occur if we propagate forward this effect from the controller, the first one, which was a wrong position sent to the motors. And this in turn can occur, we said, because of faults in the camera, like uncalibrated camera, or loose wiring in the encoder. So now that we drawn this, we can start to formalize it and prepare for the logical computations by defining effects, fault effects matrices at local level. So we have the matrix for the encoder that is a diagonal matrix because the first fault is causing the first effect, the second fault, the second effect. Similarly is the matrix, the local matrix of the camera. First fault, first effect, first fault, first effect. For the controller, the thing is a little bit different. We have that, the second effect from the camera or the first from the encoder is causing the first effect out of the controller. Or we have that the first effect from the camera or the second effect from the encoder are causing the second effect out of the controller. So we have this kind of definition from the local metrics from the controller. And finally, the metrics for the picker is the first effect we said is caused by any of either the local fault or the effect. So we have 1, 1, and 1 in this rule. But for the second effect, we said only the first effect propagated will cause it. So we have 0, 1, 0. So this is just mapping these patterns that you see here of dots and lines to ones and zeros in the local matrix of each component. Now, the tedious but simple job is to take these matrices, do the computations, do the substitutions, and get a final expression. The computations are a bit lengthy, so I will not go through every one of them. You will see in the slides, but basically you start. You start at the higher level with the picker. So the effect on the picker is the matrix of the picker that multiplies faults of the picker and effects propagated by the controller. Similarly, controller, matrix of the controller that multiplies effects that comes from the camera or effects from the encoder. We don't have local faults for the controller. Then you also have the effects out of the camera and the effects out of the encoder. And they are both basic low-level components. So here you have only local faults that are multiplied by the local matrix. Okay, so first iteration, we take what we have here for EP, and we replace the effect of the controller with what? With this. And so we have this part. And so we get faults that are local to the picker, effects from the camera, effects from the encoder. And then you need to go further and expand this part here. So in the next part, we are taking indeed the effects from the controller, and we expand it like that. So when we do this further expansion, we see that the effect in the picker is the matrix of the picker that multiplies this block diagonal matrix, where we have the matrix of the controller that multiplies these other block diagonal matrix with the matrix of the camera and the matrix of the encoder. So if we had even lower level components, we will have also here other matrices that have this shape. So identity here and a block diagonal part here. But luckily we have only 3 levels. So if you go through all these final computations, you get in the end this expression. This expression that is in terms of faults from the picker, faults from the camera, faults from the encoder. And the size of this vector is 5, because we have 1 fault in the picker, 2 possible faults in the camera, 2 possible faults in the encoder. So you just need to do this computation in order to get the final matrix of the entire system, explaining the effects and faults relation. And this final computation goes smooth, like this, and in the end you get this expression. So you have a row with only ones, and a row with some ones and zeros, which tells what? Something we could have imagined from the structure of the system. So the first effect on the picker is caused by any of a fault on the picker, one of the 2 faults on the camera, or one of the 2 faults on the encoder. While the second effects on the picker can be caused only by the second fault on the camera or the first fault on the encoder. And so in this lecture, we introduced 2 formal tools for propagating faults from lower level components up to system level. The first one, fault tree analysis, that tells us if and when a fault is propagating, and the fault mode effect analysis that tells us how and why a fault is propagating. In the next week, we are going to have another set of lectures on a different topic on change detection algorithms.